So this video is going to be about considering the force as a function of time versus considering a force as a function of distance. And so what we found in the past was when we were looking at force as a function of distance, we concerned ourselves with the work-energy theorem. But now when we're thinking about force as a function of time, what we're going to be doing is we're going to be considering it in the context of impulse and momentum. So to lay out what we had before when we were considering the work-energy theorem, what we did was we said that the work net, which is going to be equal to the integral from R1 to R2 of F net dot dr, is going to be equal to the change in kinetic energy, which is going to be equal to 1/2 mv2 squared minus 1/2 mv1 squared. So if we were to plot some force as a function of x, what we would do is we would have on our y-axis, here's our force as a function of x. On our x-axis, we have the force, we have the position. And so if we had some arbitrary force here represented, if we wanted to find what the work was here, what we did was we said that there are these tiny little segments along the x-axis that are given by dx. This is the height of the function f of x. And if we wanted to find some tiny little bit of work, so we say some tiny little bit of work, this is going to be equal to the product of f of x and dx. Now, we're considering here that this is going to be one-dimensional only along the x-axis, but this does generalize if we did want to consider this to be a vector. And so ultimately what we had was a way of describing the work, the total work, as the sum of all of the force acting over some interval. We could also say, in the case of some potential energy, that du is equal to minus f of x dx. And we can rearrange this. So we could say that if I want to find the force as a function of x is going to be the negative time derivative of the potential energy. So one way that we can see how this works is if we consider the potential energy of a spring. So u of spring as a function of x is going to be equal to 1/2 kx squared. If we do d by dx of 1/2 kx squared with a negative sign, this is just going to end up giving us minus kx, which is what we know is the force of a spring from Hooke's law. Okay, so the whole reason why I'm showing you this is that we can go forwards and backwards between the integral and the derivative definitions of these physical quantities, and it ultimately ends up being really helpful. So now what we want to do is we want to consider same kind of idea, only instead of having the force as a function of time, instead of having the force as a function of position, we have the force as a function of time. So let's draw another curve here just to denote that these are different. And we can have the same idea here where we have now some interval here, this tiny little interval dt instead of dx because we're along the t-axis, and some height f of t. Okay, so we can talk about the tiny little piece of this as the product of f of t and dt, right? So we're forming some tiny little area. And the tiny little area that we have here is ultimately going to be called the momentum. So some product of the force as a function of time and some tiny little segment of time can give us the momentum. And we can integrate this over a range of time. So say we start from some time t1 and we want to go up to some time t2, and we're applying some force over this time. What we can do is we can say that the change in momentum is going to be equal to the integral of f of t dt from t1 to t2. And we could even make this a vector. This is what defines the impulse. So the impulse is a change in momentum, which is provided by a force occurring over some period of time. And we can add up all of the little slices of this in order to find the total. Okay, so we're just doing an integral. Now we can write this in a different way. So instead of integrating this, let's rearrange it by dividing both sides by dt. And so what we end up seeing is that f of t is equal to dp dt. And we could make this a vector if we wanted to. Okay? And ultimately what we end up seeing here is if I treat this as a sum, the sum of the force as a function of time is going to be equal to the sum of the momentum as a function of time with a time derivative acting on it. So what this says, if we define the momentum as the mass times velocity, which is fairly intuitive if we think about momentum and the way that we use the word colloquially, the larger the mass of something, if we fix the velocity, the more momentum it has, or the larger the velocity two objects might have if they have the same mass, the larger the momentum. Okay, so here what we can do is we can take this and we can plug it back in here, and so we say that the sum of the forces is going to be equal to d by dt of mv, and this is going to be dm dt times v plus m dv dt, where dv dt is what we know is the acceleration. And so this says that the sum of the forces acting on an object is going to be equal to the time rate of change of the mass times the velocity of the object, and in principle as a function of time, plus the mass times the acceleration. Okay. Now, if we have some object where the mass isn't changing, then this reduces exactly to Newton's second law. So the sum of the forces is equal to mass times acceleration. And this is something that we know already really well. Now, the case where this term can come into play is when we have something where the mass is going to be changing, like a rocket. So a rocket's propelling itself by ejecting gas, and so the mass is going to be changing. So we have actually a more general way of expressing Newton's second law if we write it in terms of a momentum, or time rate of change of momentum, than if we do in terms of an acceleration. So that's the first part here, thinking about how we can get to Newton's second law by considering these integrals and the way that we can reverse integrals. And when we think about infinitesimals, tiny little pieces, and thinking about derivatives. Okay, so the next portion that we're interested in is considering the difference between two forces. One, where I have a force as a function of time, where this is going to be equal to, I think this one's going to be the a times t. So force is a function of time, a t is equal to capital A times t, versus some force as a function of distance, where I'm saying this is going to be the force F sub b, which is going to be equal to b times x. Okay. And what we'd like to do is we'd like to find what the velocity of an object is going to be after it's gone a certain distance, having one of these forces applied to it. So we have, here's some distance that we want to go, some distance of d. Okay. And what we want to do is we want to find what the velocity of this is going to be if I apply the force Fa, or if I apply the force Fb. So what's the difference between these? Have the same mass, and we want to go the same distance. Okay. So let's first look at dealing with our Fa. Okay. And the really first part of this problem is to do some dimensional analysis to determine what the units of capital A and capital B are. So we can see that the units of capital A are going to be newtons per second, right? Because that's dimensionally how this is going to work out in order to get us units of force on the left and right side. And the units of B are going to be units of newtons per meter. Okay. So let's start with looking at how we can find what the position as a function of time is and what the velocity as a function of time is for Fa. So with Fa, what we have is this equation for the impulse. So I vector is going to be equal to delta p, which is going to be equal to the integral from t1 to t2 of a t dt, or more generally, just to write down our original equation, is this is f vector t dt. We're taking this f vector to be one-dimensional, and so this is going to be the integral from t is equal to 0. So we're starting our clock at the beginning to some capital T, or some t is equal to just t, lowercase t, times a t dt. Okay, so this says then that this is going to be a t squared over 2. Okay, and this is going to be equal to the change in momentum. Now we said that we start with some velocity of 0, and so really this is going to be p as a function of time minus p at t is equal to 0, but we're saying that this term is 0. Okay, so we have then that our momentum as a function of time is going to be equal to a t squared divided by 2. But we know that our momentum is just going to be our mass times velocity, and we're assuming that this is going to be something that has a constant mass. And so we could really write our velocity as a function of time to be a t squared divided by 2m. Now, if we want our position as a function of time, we can say x of t is equal to the integral of phi of t dt, because dx dt is going to be, by definition, phi of t. We multiply both sides by dt and integrate to get our x as a function of time. Okay, so this says that this is going to be a over 2 t squared over m integral dt. And so this is going to be a over 6 t cubed divided by m plus the constant of integration. In general, what we're going to say that that's going to be equal to 0 because we're choosing our coordinate system so that we're beginning at t is equal to 0. Now, to find what the velocity is after we've gone this distance d, this is just applying kinematics now. So we say that we want to find x of t is equal to t star, some special time that it takes in order to get that distance is equal to d is equal to a divided by 6m t star cubed. And then we can solve for t star. So t star is going to be equal to 6m times d divided by a to the 1/3. And then the velocity at d is going to be the velocity when time is going to be equal to t star. And so this is going to be equal to a divided by 2 times m times t star squared, which is going to be a over 2m times 6md divided by a to the 2/3. And then this is really to the 3/3. And so we can bring this on the inside here, and ultimately we're going to be canceling some factors here, because really you could rewrite this to say that this is going to be a over 2m to the 3/3 times a over 6m to the minus 2/3 times d to the 2/3. And so we can get rid of some of these terms so that we end up having a 1/2. We have a 1/6 to the minus 2/3. This can become an 8 to the 8. This can be an 8 cubed. So this is going to be this could be an 8 to the 1/3. So this is an 8 to the 1/3. So, and then this is going to be a over m to the 1/3, d to the 2/3. And so effectively what we have here is, I'm not so happy with the way that I'm combining these terms here, but at the end of the day, we end up having something that is going to look like 1/2 times a 6 to the 2/3, or let's do it like this. 1/2 times a over m to the 1/3. I flipped the 6 over here, so this ends up being a 6d to the 2/3. Okay, so this is what our velocity for a is going to be when we get to the distance d. Okay, so barring any arithmetic mistakes, so I think this should probably be fine. D to the 2/3. Yeah. So I would check this. Because I'm doing it very quickly, but this looks pretty good. Okay, so doing this for B is actually a little bit easier, because what ends up happening for this is we just have f sub B is going to be equal to Bx, and now we're applying the work-energy theorem. So the work net is going to be equal to the integral from R1 to R2 of Bx dx, which is going to be equal to, we're going from 0 to d, so this is going to be B d squared divided by 2, which is equal to the change in kinetic energy, 1/2 mv d squared, minus 1/2 mv0 squared. And we're saying that this is going to be 0. And so at the end of the day, what we end up having, we can cancel our halves. We end up seeing that Vd for B is going to be equal to B divided by M square root times this is just times D. Okay. So I'm just checking my units here, because B is going to be kilogram meter per second squared. We're going to cancel, sorry, we actually, it's kilogram per second squared, because it was Newton per meter. And then we have a mass that's going to cancel this. Square root of 1/seconds gives me 1/second, and then we have a D here as well. So just for completeness, just to check to make sure that I didn't make any mistakes, at least for the units on this one right here. So we'll just do our dimensional analysis really quickly here. So this ends up saying that this is going to be, this is newtons per second meter times, or to the 1/3. So this is going to be kilogram meter per second squared, but this is going to be per we're canceling a mass, sorry. So this is a kilogram per kilogram per second, second squared. We have a meter. So then this is going to cancel here and here to give us, this is to the 1/3 times a D to the 2/3, which is going to be meters. So we have, this is going to be meters to the 2/3, and then that's it. And then we have meters to the 1/3 times meters to the 2/3 divided by seconds to the seconds cubed to the 1/3. Okay, which gives us units of meters per second. So this should be correct. Okay, so that's going to be it. This is just a nice quick way of seeing how we can compare the usage of force as a function of time and force as a function of distance. All right, take it easy, guys.